It's a real great pleasure being here. And so I'm going to be here for the next 2 days, and I'm looking forward to meeting a lot of you. And so this should be lots of fun discussions. And so I like to begin my talks with actually a picture. And so here is a scene that you've never seen before. Maybe Joseph has seen it since I've been using it for a lot of my talks. But it's certainly a place you've never been to. And despite that, you actually have a very good idea of what's going on in this scene, and you have a very good idea of the structure of the scene. You understand it really deeply. And as a concrete demonstration of this, I want each of you to imagine the man behind the counter gets milk from the fridge. So in the next few seconds, maybe the man goes to the fridge and gets milk. So think about what would have to change in the scene in order for that to happen. So I hope you should be able to do this because it's a fairly simple task, but let's just go through it together. And so we have the man behind the counter, we have the fridge in the back of the kitchen, and the man is going to have to walk to the fridge. And I hope all of you realize this. He has to walk through the scene to get there. And then when he gets to the fridge, he's going to have to reach out and open it and then reach inside and get the milk. And so this is an incredibly boring hypothetical. I hope this is the most boring hypothetical you've been asked to consider at the start of a talk, because this is something like a child could do, even like a dog or a cat could do. But it's actually kind of amazing that you're able to do this. And the reason why it's amazing is that this picture doesn't contain that information. So if you actually look at it from this single image, it's just a collection of intensity values on a 2D grid. And there's no actual information that all of you can see in this image. And that's not intrinsically present in the image. And so humans have this amazing ability to extract immense amounts of information from even as little as a single picture. And the goal of my research is to get computers to be able to extract the same level of understanding, to be able to understand scenes as a place where you can move around and do things. And so, of course, there's a long way to go on this, but I'm going to talk about two things I've been particularly interested in recently today. Basically, how do you move around scenes and how do you do things in scenes? And sort of understanding these things, especially from sort of small amounts of images. And by understanding moving around scenes or getting places, I mean that when you look at this picture, even though you don't have a full 3D model, even though you've never been here, even though this is a single 2D image, if I say, go to the refrigerator, you would understand that you move the chair a little bit. You can walk around the man to get there. You could also walk around this other guy and this woman and then go to the refrigerator. And you can do this even though you can't see the floor behind the counter. So you have this ability to infer from a very small amount of information. You can make inferences about this larger 3D context. And so I'm going to talk a little bit about work that's trying to infer how to move about in images with a small amount of information. And I'll discuss more specifically what we're doing. The other thing that I'm interested in is if you have like this refrigerator, like you understand lots of things about it. Like I know how to open it. I know there's this dark thing on the left, and that's probably some sort of thing that dispenses water or ice or something. I have an idea of what might be inside. And a computer understands none of this. So we can have a system that can detect these things. But you have to be careful and remember that like an object detection system, the way it works is it takes this part of the image and it says, OK, let's see, what is this? So it goes to the COCO dataset and it says, OK, is it category number 1? No. Is it category number 2? No. And all the way down to category number 73. And it can associate this part of the image with category 73 and with a text string refrigerator. But really basic questions that even as anyone who owns a pet knows, they understand, like how do you open it, or what's inside of it, or what happens when people open it. These things are completely inaccessible. And so one of the things I'm interested in getting computers to understand is how do you sort of manipulate objects and what happens when you manipulate them. And in particular, the big challenge is how do you get data of this? And one of the challenges I'm going to talk about is how do we obtain large amounts of information or videos of people interacting with the world with the hope that we can then learn about how the world works by observing people doing this. And so today I'm going to talk about two things. The first is navigating from images, and in particular, following demonstrations of paths. And I'll explain what I mean by that. And the second thing is learning about the world by observing humans interacting with it. And in particular, I'm going to talk about how do we gather large amounts of data for this, because this actually turns out to be a big challenge. So I'm here for the next few days, so I'm going to briefly mention what I'm not talking about today, but which we can talk about one-on-one. And so a lot of my work has been on the task of taking a single 2D image, like this, and producing some sort of 3D representation of it. So this could be like a depth map, for example. And as you can imagine, this is an under-constrained problem, because you go from 2 dimensions to 3 dimensions, so you have to recover that dimension somehow. And so there's lots of interesting constraints and learning that you can do to do that. And just as an advertisement, and as a way of illustrating why I got into navigation, actually, I'll show you a little bit of my most recent work in just terms of an output. So we can take a 2D image, and here it's actually a synthetic rendering. But we can do this with real images as well, although less accurately. And we have systems now that can predict from this 2D image a 3D representation in terms of voxels. So if you don't know voxels, you can think of this as just trying to reconstruct the scene in terms of like little 1x1 Legos. Or if you're younger, it's like making the Minecraft version of the scene from a single 2D image. And so it's not perfect. I wouldn't want to 3D print this and put it in a museum. I wouldn't want to use this on a robot. But what's exciting is that this is an incredibly hard problem because you're going from just this 2D image. And we're producing results which, although the couch is a bit blurry, we're producing results which are actually good enough where you can rotate the camera up and look at it from another view, and it actually looks somewhat reasonable. And there's a long way to go, but it's exciting that we're able to do this. But one of the big challenges that we face in this is basically we have this under-constrained problem, and we have to represent this output somehow. We have to say all the things that we can see in 3D. And we have this big representation question, which is how do you represent a 3D space? So for example, if I look at the bowl on the table, I don't know where it is precisely. I also don't know where precisely the table is. Like if I ask you to give me a translation vector for where the table is, you'd have a lot of difficulties doing this extremely accurately. But I know that the bowl is exactly on the table, and it's not floating above. And I can see this in the image. And so the big question to me is, in this 2D to 3D thing, in particular for 3D, is how do you actually represent the 3D shape of things? Because there are lots of, you can have very simple representations, but these actually don't capture all the things that you can see. And so this is something I've been very interested in terms of scenes, and I'd love to talk about. And the reason why I got into navigation is actually this, is how do you represent 3D space? And in particular, if you have a city-sized area, like for example, Prague or Paris. So I recently moved to Paris for a few months, and I can't actually observe all of Paris. But I can walk around, and by a limited set of observations, most of which are noisy, most of the time in Paris, I don't know precisely what direction I'm facing. The streets are very curvy, and the same thing happens, I'm sure, in Prague, where if you don't know it very well, you might be confused as opposed to which exact direction you're facing. But at the same time, you can actually navigate around quite nicely. And so the big question I wanted to investigate is how do you represent really large 3D spaces for which you don't have a complete observation? So basically, how can you spend a week in Paris and still have a very good idea of what's going on without having to drive a car through with a GPS and a laser scanner? And so this ability to represent these spaces is actually something you do all the time. And I'll tell you one very Parisian version of a task that humans use with navigation. But as I'll explain in a second, this is an ability you use every day. So when I first moved to Paris, Alyosha, who I know came here earlier this year, he loves giving out advice about where to go for food. And he says, go to Blé Sucré. And it's this bakery. And among other things, they make amazing lemon tarts. These are impossible to find in the US. The US tarts are too sweet. This thing tastes like a lemon. It's wonderful. And so he says, you should go to Blé Sucré. All right, so I leave INRIA. And then, so how do you get there? Well, you go to the main street. You walk past this cafe. You walk to the police station. You take a right. You get to the square. You go to this bakery, but you don't go there because that's not as good as Blé Sucré. You keep on walking. And then you walk and you hit this park. And then you take a left. And then finally, you end up at Blé Sucré. Now, I'm not going to quiz you on this. If you come to Paris, you can find Blé Sucré on your own with Google Maps. But if I did take this path, and I did take it actually on Sunday, you could very reasonably ask the question, OK, given a single demonstration of this path, like if Alyosha takes me, or if I walk through Paris with my nose in my phone like a tourist, and just keep precisely track of where I am, I could wonder, well, first of all, how do I get back? And hopefully, if I see one demonstration of it, I don't have to have someone guide me back. Similarly, I came here from my hotel in more downtown Prague, and I would have a very good idea of how to get back, and I don't necessarily need to follow my phone as precisely when I go back. And similarly, well, how do I repeat this? Well, once I've taken this path once, how might I follow this path again? And so this is an ability that you use all the time. It's not just going to find tarts or going to go find a new building in a new city, but when your friend takes you to their house and you haven't been to your friend's house, if they show you to their kitchen, they're not worried that you're going to get lost and end up in their basement or something. And so you have this amazing ability that people don't really appreciate because it's just so obvious. It's something that, as I said, a dog or a cat has this ability as well. And it's actually quite challenging if you think about it, to actually do this task. And the reason why it's challenging, I think, there are two big reasons. And the first is that actually organisms like humans and smaller animals and robots don't precisely replicate their actions. It's really hard to precisely repeat what you do. And so, you can, in fact, people in the psychology world actually study this, and you can do things like you blindfold people and you ask them to walk a certain distance. You basically walk them one distance and you have them walk back. And on the x-axis is how far they are supposed to go, and on the y-axis is how far they actually went. And if this actually worked and humans were able to replicate things, you'd actually see a beautiful one-to-one line. But as it turns out, that humans actually systematically screw this up, and on the left is distance, on the right it's how far they turn. And so humans are actually pretty lousy at this. And so these are, in fact, even distances that are more like 10 meters. And this is not like, for example, walking a kilometer. And so organisms can't actually do this just blindfolded. So they actually have some visual signal. And so you have to somehow integrate that. And the second thing is that actually, in realistic scenarios, the world is constantly changing. So when I walked to Blaise-Sucre, there was actually a nice farmer's market. It's very distinctive. It's very nice. So if I just get a tart and walk back, that's a very good idea of knowing which street to turn on. That's a very good signal. But if I stayed 8 hours until it was night, well, if I go back to the same place, this farmer's market is gone. And actually, basically, the most interesting stuff in this image is not useful anymore. It's actually not a useful localization cue. And so actually, the useful signal, which is how do you actually identify this corner, is a little tiny name on the sign, which is the name of the restaurant. And that's actually how I identify this street. And so you have to be able to figure out what changes and what doesn't. And so these are, I think, the two main challenges that I see in terms of this task of following paths. And so we worked on this problem at Berkeley, and this is the lion's share of the work is really done by two guys, Ashish Kumar and Saurabh Gupta. And so this is a paper which is appearing at NIPS, where this year's NIPS, and it's with Sergey Levine and Jitendra. And it's basically how do you follow paths robustly. And to be more concrete, the task is we want to follow a path either forwards and backwards, and we're given a single demonstration of the path. So we can't just have a tour guide take us through Paris 100 times. And we have, during the path, we have an observation, an image. We have the action we took, and we know the pose that we were at during the path. So you can imagine this is like going on a path with an expert, or you're walking around with a GPS system. Now, the two challenges we have is we have a noisy actuation model, so we don't actually repeat any of our actions, and the world can change on us. And one thing I want to point out is that even though we have the pose at demonstration time, when we actually execute the path, we don't have this. We're just doing it from images alone. And so this is a navigation problem, and there's, of course, navigation is it's as big of a field as recognition, if not bigger. And so by navigation, this could mean hundreds of different things, and there are tons of different problems. And in the interest of time, I'm not going to explain the related work for everything, but I'm just going to paint with very broad brushstrokes, like the two main approaches that people have taken. And I apologize that I'm not doing justice to this. And so the classic way to do it is to build a map and to plan on top of this. And so you can, there are well-established techniques for taking a set of images and building a map of them, basically building a 3D model. And similarly, in robotics, there are well-established techniques for taking a map and planning a path through it. And these are wonderful. It's at the level where people have written textbooks on these. And this is a very effective system a lot of the time. It's not perfect, but it's a quite good strategy for doing this. There are two things that are, I think, an issue with this approach, where you build a map with geometry and then you plan on top. The first issue is that it's actually really difficult. It's actually a very difficult problem to build a 3D map. So if you have a single path, building a precise 3D map that actually is metrically accurate is quite difficult. And it's a challenging problem. And the other thing is that they're not jointly optimized. So the planning step and the mapping step are two entirely independent things, and they're just joined by having a beautiful 3D map. Which means that the map mixes really important stuff with the not so important stuff. So like, for example, in the navigating to Blaise-Sucre example, you might have the headlights on a car beautifully reconstructed, or you might have the exact shape of the car reconstructed. That's actually not a useful thing for navigating. And so it can't actually focus its attention on the right bits of the scene. The second thing is that people have, of course, done this with very much end-to-end learning types of situations. And so actually end-to-end learning of navigation has become a hot topic in computer vision and machine learning. And so there are lots and lots of works that do this. The particular task we're solving is actually, I think, fairly unique in the literature, because we have a single demonstration, which is typically a lot of these scenarios require millions of demonstrations of a known scene. And so we have a single demonstration of a new scene. And we also have noisy actuation and a changing environment. And these are actually very important, because these are, as I'll explain, these are actually quite important for evaluating methods properly. And so as far as I can tell, we're actually so far at least, or at least at the time of submission, we're the only people who are tackling this particular problem of given a single demonstration and having noisy actuation and a changing environment. And so precisely, to also give context, the agent that we're dealing with is not going to be an actual physical robot. It's going to be sort of like a point agent that sort of has a number of macro actions. So we're not doing joint torques. So ideally, what the agent can do is it can move forward, like, for example, 40 centimeters. It can turn left. It can turn right. And so it has these sort of discrete actions. And so we're abstracting away the actual process of moving forward. And so this is sort of an ideal agent, and you can imagine we might study this with this ideal agent, and this would be wonderful. But there's a big issue, and the first of all is that this is not biologically plausible. But the second issue is that actually from an evaluation perspective. So can anyone think of a really simple baseline, like the dumbest thing possible, that actually gets 100% results on this particular task of retracing a path given a demonstration? Like if you have no noise. Like what would be like the dumbest thing you could do? Like if you compare images, or it's even dumber. It doesn't even, you can in fact do it blindfolded. If you have a demonstration of the path and the actions you took. You just repeat the actions, and it works 100% of the time. If there's no noise, it's kind of like some sort of like, I don't know, like a Mr. Bean movie. You just repeat your actions and it just will perfectly work. You'll just move. If the world doesn't change, if the actions are noiseless, you just like exactly move through everything, and it'll be beautiful, and everything will work happily. And of course, in real life, if I just repeated the actions of going to Blaise Cray, I would probably get hit by a car, or I'd like bump into things. And so you can't actually do this. But so it's actually important that you have noise. And so the agent that we have actually has noise. And so when it tries to move forward, it actually rotates a little bit. And then it moves forward, but not the precise amount that it wants to. And when it turns, it actually turns, and it has noise in the turning. So this is actually a reasonably hard to control agent in the sense that there's sort of like about 20% noise in it. But this is, it's certainly feasible to do. And as you'll see, the system is able to do it. OK, so that's sort of the setup. And so how do we actually solve it? And the way that we solve it is that we have an abstraction of the path. And what we're going to try to do is we're going to generate some sort of numerical abstraction of this path. So we have these images, we have these actions, we have these locations, and we just need to turn this into a big matrix that some machine learning method can use. And then we take this abstraction, and then we're going to stick it into some sort of recurrent model that will take in images as an input and produce actions as an output. And so this is the sort of big picture of what we're going to try to solve. So you have an abstraction, and then you have something that can use this abstraction to make decisions about what to do. And I'll explain each of these in turn. So the abstraction is going to be quite simple. So we have each step of the path. You have an image, you have an action, and you have the location of where you are. And so the action and the location you can just represent as numbers very easily. The image, of course, you convert into a number using a convnet. And so we just use a simple 5-layer convnet. And so there's nothing particularly remarkable about this. But it just produces a set of final features that are just like a feature vector. And then so each step in your path is going to be image features, the action represented as a vector, and then the location. And you stick these all into what you would call like a memory vector. And this is just the memory of what you did and what you saw at that location. And then you have the entire set of memories along your path, and this is a big matrix. And so you can convert this path into a nice matrix that machine learning is very happy with.
So maybe again, so you store the observation, the feature observation, and then the action, and these.
Sorry, P is the pose of the robot. And so you have the basically in it's in, I believe, absolute coordinates with respect to probably the start of the path, but it's just some sort of representation of the pose. Yeah, so it's just like a, I guess, x, y, theta type thing. So you have this big matrix of all these things, of basically the pose, the action that you took, and the image. And then you're going to have a recurrent model that's going to follow the path. And the way that this works is the specific recurrent model we use is a gated recurrent unit. So it's just, you can just substitute this with a recurrent neural net. And if you haven't seen this before, you can just think of this as just something that you can learn through time to basically train to do stuff on sequences. And so it's just a network that works on sequences. And so the way that this works is it has to look at the memories in order to make decisions. And we don't want to look at the entire memory because when I start walking to Blaise-Sucre, it doesn't really matter like what the park looks like. I just need to figure out where to get to the first turn. And so we have a pointer which points to where we're looking at in memory. And so you can think of this as just like an attention mechanism. And then you build basically a Gaussian function around it. And so this is sort of like a soft attention. And this produces weights on the memories, basically which memories are most relevant. Then you basically do a weighted combination of your memories to produce basically your memory vector at that point. So basically this is just a way of looking at multiple memories at the same time. And this is, of course, all end-to-end learnable. And so this memory vector goes into the network. And then the state goes into the network. And then the observation goes through a convnet, which produces a feature vector. And that goes into the network. And then the network is going to have to basically look at the memory, look at what it can see, and look at what its state, it can keep information about the previous state in this state vector. And then it has to decide on an action. So this is what it predicts. And so this is just like a discrete choice. And it's also going to have to update the state vector and the attention vector. And so it just has to produce an update to where is it looking at in memory, and I'll explain how the recurrence works. It also has to produce an update to the state. And one thing I want to point out is the important thing is that actually, even though we have like the pose at path demonstration time, the way that the system interacts with the world is it takes in observations and it puts out actions. And that's the only means of communication with the world. So it's basically purely visual, and it just does an action. So we have a recurrent model, so we have to set up the next step. So the way that it works is that you simply, you plug in the next state into the state vector. And then to update your location, what we do is we have basically you provide an update to where you think the memory pointer should look at. And what we found is that we can basically put this through a sigmoid. So this just squashes the outputs. So basically the outputs, it updates the memory by either staying at the same place or moving forward one in the sort of index or somewhere in the middle. So it can basically produce some sort of thing. It can either basically move forward or stay at the same place or do something in the middle. And so we experimented with a number of things, and this seems to work the best because it makes it very easy to either sort of stay in place or move forward because you just have to produce a big value or a small value.
That is output from the GRU.
It's an output from the GRU.
To move along
exactly how to move. So it controls what it's going to look at. And so it has to, in the end, produce a set of attentions that point at the right thing in order to make the best decisions. And so it gets updated. And again, all this ends up being a very complicated, but it's an entire end-to-end system that you can actually train from images. And of course, it's a big, long, complicated network, but you can convince yourself that everything is differentiable, and you can just all the components can be put together. And so we of course have to train it. And what we do is we train it by imitation learning. So we experimented with reinforcement learning, but we found that we couldn't get good results, or at least we couldn't get good results with the amount of training time we were willing to spend. And so it takes a while to train this sort of model. But you can just train it to predict a sequence of actions so that each time you're making progress on reducing so that overall you make a lot of progress on reducing your distance to the goal. So anything which moves you forward is considered a positive, basically moves you towards the goal. And you have to make predictions that over the sum of the entire sequence, on average, move you very close to your goal. And so this is the way that we train it. There might be other ways to train it, but this seems to work. And it turns out that we don't run into too many issues with this imitation learning scheme. This is just simple supervised learning. And then yes?
Just a question on this slide. So what is the role of the recurrent unit? Because it's not kind of representing the input.
So it has to, there's a hidden state, which basically lets you do things like if I'm trying to walk around this table, there are basically, I can't come up with an example off the top of my head, but you can come up with examples where you basically turn, and the best way to make progress is actually to turn back. And so if you don't keep track of state, you can't do things like say, OK, I'm going to take a detour. Because typically detours cause you to go backwards, basically make less progress. But in the end, over the entire sequence, they produce more progress. So you end up in these sort of like weird flipping back and forth situations. Yeah, it allows you to make long-term decisions that are not sort of greedy. And so I don't have the numbers because it's actually right before the NIPS camera-ready deadline. So the numbers are all scattered all over the place. And I don't want to show numbers that are not going in. But we have a lookup baseline. And the lookup baseline, which is just you don't have any state, that doesn't do too well. Because typically you always have to make progress, you have to take one step backwards and 2 steps forwards, typically.
So like a simple forward unit here just wouldn't work as well.
Yeah, exactly. So a simple sort of reactive policy doesn't work very well. Or at least on the stuff we tried.
I don't understand why there is this sigma function or this sigma something. So why there is not just increment?
So you could make a discrete. OK, so if you just did increment, so the network needs to be able to control whether it increments or not. If you do a discrete decision, then you have to back propagate through the discrete decision, which is a bit hard. I mean, there are ways to do it, but then you have to do this thing where you do the sampling trick. And so it's a way where it's, in practice, I don't know precisely how many times it actually uses the ability to move forward 0.5 as opposed to 0 or 1. In fact, when we played around with different variants of the function, it turns out that actually making it easy to do increment or decrement is actually quite important. So actually, if you allow it to jump forward 5, it actually has a hard time because it can't precisely produce just move forward 1. But here it's very easy it's just entirely differentiable, and it's you're not going through a hard decision, which makes things easier. Any other questions? OK, so then I can show some results. But the one thing one little detail I have to show is that actually returning home is kind of difficult because the visual features look different. So if you go forward past this restaurant, it looks different than going backwards. And so there's something which we have to do. And the fun thing about this, I mean, this is actually a very difficult recognition problem, like a location recognition problem. And what's fun about this entirely learned system, I'm not saying that this solves this problem exactly. But what you can do is you can build a network that is supposed to compensate for this. It essentially can learn to overcome this. And what we do is we just simply imagine what it should look like from a different angle. And you can train a system end to end to produce memories that when you execute them through this network will actually produce the correct results. And so we essentially imagine what the feature should look like. So we have our memories, and we have the image, which corresponds to these memories, and we have the relative pose. So we're trying to imagine at the query location Q, we're trying to imagine what does it look like. And so you can basically produce a feature which says for every single memory in my path, what's the relative pose? So what's the relative angle and the relative location? And these guys are just a feature. And then you can train a neural network that will take these features and will produce another feature vector so that when you sum them all up, this produces a final memory, imagined memory. So this is essentially, if you squint your eyes at this and forget about the details, what it does is it looks at the memories and it looks at how close they are to the query location where you're trying to imagine. And it figures out whether the memory is relevant and how to transform the memory. So for far away things, it will just say 0. And for the nearby things, it will try to do things like say, oh, the left-hand side of the image should switch to the right-hand side of the image. These sorts of things. That's what it should do. And so you can actually train. But the cool thing is that it's a network, so you can train this, and you don't have to worry about this really actually very tricky problem of how do you imagine what something looks like from another view. Because this is just like a very difficult and hard to solve problem.
If you did have a 3D model,
yes,
you could do these things.
Oh yeah, totally. Yeah, and one thing I want to say actually with this is that I'm not saying that this network magically solves all the problems, and we compare with more classic methods and based on building 3D models, and we do about as well. I think this is just a different way that has different properties, and so a 3D model automatically solves this. In fact, that's the beauty of 3D is that you don't have any of these viewpoint issues. You can you can get viewpoint invariance for free. Okay, so experimentally, what we do is we test on 2 different environments. And what I want to emphasize is that we test on held out data. And so right now in navigation, there are lots of different protocols floating around, lots of different things that people do. And one thing which is important is that we're testing on held out data. And so here we have the Stanford building data set. And this is a 3D scan of a bunch of buildings in Stanford. And so it's realistic in the sense that these are actual images that you can then render from other angles. And so it's actually like a real environment. And so this is quite nice. The other thing we test on is a data set called SunCG. And this is a graphic environment in the sense that it's a bunch of models placed in a bunch of rooms. The rooms were created by humans for the purpose of redecorating houses. So this layout is quite good. The models are OK. But the reason why this is actually useful is because you can remove a model, or you can add a model. You can change the environment without leaving artifacts that a network will pick up on. So if we take the Stanford building data set or any other data set, and we just start adding obstacles, the network will very easily figure out, wait a second, this obstacle has been added, or this obstacle has been removed. So they can use that to cheat. And so this is the artificial environments are a nice way to actually control this. So we have a bunch of different baselines. As I said, it's right before the NIPS deadline, so I'm only showing you the results which are going to go in the paper. But things are still going. But the baselines that I think are very important to have, we have an open loop baseline. So this just replays the actions in forward or backwards. And this seems like a really dumb baseline. But actually, if you're just walking down a hallway, this baseline in expectation actually gets the right answer. So it's actually not as dumb as you'd expect. And it does depressingly well. And people don't really compare to it that much. And I think it's important to check to make sure that the learning is actually necessary in your setup. And the second one is a classic method, which is based around CoalMap, which is a nice package of basically geometric algorithms. And so we reconstruct using SIFT. We localize using SIFT. And then we basically use the ground truth action that we know to basically take the optimal action. So there's this entire mapping and planning procedure. And here we're not worrying too much about planning. We just have sort of an oracle planner. And then when localization fails, we just rotate in place, which we've been told is a standard strategy for trying to find where you are. And so I'm not saying that this is like the best method for reconstructing, for doing this geometrically. I think that's an open question, and I'm hoping as a field we can figure out how to do a head-to-head comparison and actually get good answers. But this is, I think, a reasonable proxy for some of the stuff that people are doing with geometry. So we can take the Stanford building data set and look at it from above, and we can just watch what happens if we replay the actions. And so on the left is this open loop replay where we just move forward and we just execute the actions just blindly. And so it's going from the red dot to the red star. And so you can see that this is an overhead view. The robot doesn't have access to this. But it's trying to get into an office, and it's actually very difficult to do this. So even in an office environment, you have to precisely go through the door. And on the right is the proposed method, which actually is able to, even though you can see, in fact, you can see the amount of noise on the left. So it's actually navigating a robot that's, it's not a very smooth and elegant robot. It's sort of, it just makes these jumpy things, and it just doesn't exactly go where you want. And yet it's able to navigate reasonably through the door a lot of the time. Similarly, we have the open loop replay on the left. And here it's trying to go through this hall and then go into the door. And again, it doesn't work too well. And of course, you can control the noise, and we have some experiments on controlling the noise as well. And then on the right is our method, and it does reasonably well most of the time. So it doesn't always necessarily get all the way to the goal, but it gets pretty close. Yes?
Is the maps, is it the Stanford data?
It's the Stanford data, yeah.
And the fact that they are kind of mostly filled is the furniture, which is in the
The furniture, yeah, the furniture is a big issue because you kind of like bump into it and then never really move, or sort of like move along and then get stuck somewhere else. So it's actually, even though it's an office, and offices are kind of easy, you can get stuck pretty easily. And then quantitatively, the proposed method gets like far better. And so at least on one of these experiments, you can typically you have something like 84% success rate for our methods, and this is with a certain noise level. And on the other hand, open loop replay gets something more like 20 once you start adding a lot of noise. And then so I'll show you a video of actually what you see as the agent. And so here is on the left the overhead view. And then here you have the reference trajectory. And so what it's going to do is it's actually going to go backwards and follow this trajectory backwards. So you walk out of the office, and then you're going to go through the door. The important thing to mention is that these environments are actually quite clean, but that's actually a bit of an issue because you can't just say, oh, I'm just going to go to the nearest door. Because actually there are 2 doors, and you have to figure out which one to go into. And so you have to replay that. You have to remember which one actually you go through. And on the right is going to be the method that we have. And so it starts off where you end. And so it doesn't go into that door. And then it's going to actually sort of walk past that door. And you can see it also has a limited field of view, so this also makes the navigation a little bit more difficult. And you can get a sense of basically how smoothly it's moving, that it's a somewhat difficult to control robot. This is not like sort of moving around in a first-person shooter game. If you had to work on this robot as a grad student, I think you'd be very unhappy, and you would ask your advisor to buy you something else. And so you can see that it does a reasonable job of getting back to where it starts. Yes?
So the task is always going backwards?
It's going backwards or it's going forwards. Going forwards is kind of a bit boring because you just repeat the path. So I figured I'd show a going backwards one.
So you do both?
You do both, exactly. And you can test both. And so going backwards is, of course, harder. And I'll show some numbers as well. And then what's fun is you can also do you can change the amount of noise that you get. And then you can look at the success rate. And success here is basically, do you get within a certain radius of the goal? And so if you have 0 noise, basically blue is open loop, and this is just replaying stuff. If you have 0 noise, you get 100%. And green is slam, and red is the proposed method. Unfortunately, red-green is not a good contrast. But you can see that the proposed method in the sort of slam-based system, which is learned entirely, actually are relatively competitive on the Stanford dataset, which, as it happens, has nice, beautiful textures. And then we have some visual servoing baseline, which doesn't do as well. But the other thing to notice is that the open loop thing systematically goes way, 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 way worse with increasing noise. One thing you can do is you can change the
noise level? So
the noise level, basically.
How much should I imagine? Kind of what is 0.5?
Sorry, 0.5 should be, it's the fraction of, so basically 0.5 is really hard to control because it's moving forward 40 centimeters plus or minus like 20. So it's basically, it's impossible. So it's actually, it's something where if I had to do it, I'd just give up. I say, this is stupid. I refuse to do this experiment. But if you're a machine, you can do this without getting frustrated. So you can have a changing world. So here on the left is overhead again, and this is the SunCG dataset. In the middle is the reference trajectory. On the right is basically what happens at test time. And here we've added a bed. And so, of course, if you do open loop, you're going to bump into the bed if you actually manage to execute the trajectory. And so you can see it has to sort of go precisely through this door, and it's going to walk over to the shower. Now, what you're going to see is that the method is able to navigate around the bed. And so we didn't teach it to navigate around objects. This is just emerges out of the fact that you're supposed to get to the end goal. And so this is, it's a nice emergent behavior, and to some extent, it's like not surprising that it learns to do this. And it's an ability that like really basic organisms have. They don't like to bump into things. And what's fun, though, is that this emerges out of the fact that we force it to work with environments that change. So we didn't engineer this behavior. We just gave it in a lot of data where you have added obstacles. And it comes up with this solution, which is to actually have a thing that navigates around stuff. And so what's nice is that instead of designing modules of a method, you're designing the data. You're adding the variants that you want. And so it's, in some ways, maybe it's not as effective a way of getting robustness. And here it gets basically to the shower and kind of like moves around to try to make sure it's in the right location. It doesn't have like a stop button to say I'm done. And so, but what's cool is that instead of designing stuff, you basically design it in the data. And on this like less realistic data in terms of like, there's not a lot of texture, you can actually sort of look at the classic method and the proposed method. And so if we just use the standard trajectories, we don't do anything like adding objects or anything. We do much better, in fact, because probably there's not very much texture for SIF to latch onto. So this is not entirely surprising. But what's cool is that the method works on both this textured environments and this untextured stuff. And then if we add objects, performance, of course, drops for both, but our method is still actually able to handle these added objects. And again, I think the very interesting thing is you design, rather than designing the method, you design the data. So you add the variants that you want it to be robust to, and then this makes it nice. This makes it work. OK, so that was basically about our navigation efforts. And so this gives us a way to go to the refrigerator and back. But I promise you that we'd be able to understand things like this. And so basically, how do people interact with objects, and how can you interact with the world? And so an idea which goes back to actually when I was first started my PhD and I was working with Joseph and Yvonne was the idea that if you want to learn how this kitchen works, you could simply watch people manipulate it. So if you want to know what can be opened, what can be picked up, you can watch this woman manipulate the scenes. And so just by observing things, you can figure out how the world works. And so this is an idea that I've been chasing ever since. It's a really cool idea. And Joseph, I think, described it as having people as active sensors. Like you sort of send them through the scene, and they're like a Kinect that can open things. And so we had this paper in 2012, this set of papers, where we watched people on YouTube, and we tried to figure out what people can do. And at that point, pose detection wasn't so good. So we tried to figure out where can people sit, where can people stand, and where can people reach and touch stuff. So these are just heat maps of what you can do. And so this is aggregated over an entire big YouTube video. So it's basically a sittable detector. And you can do all sorts of stuff with this. We can do geometry. We were trying to predict rooms as boxes. We were trying to describe it as one big cube. And so if you just look at appearance, it doesn't work so well. If you look at where people can sit, you can actually improve the estimates by making the room bigger. You can also, for example, figure out what is an object by how people interact with it. If someone sits on something, it's probably a chair or a sofa, and it's not really likely to be a dining table. And so you can actually use this to figure out the semantics of objects as well. So I wanted to revisit this idea when I started my postdoc. Basically, I looked back on the two main hurdles that we had faced when doing this original idea of watching people to figure out how the world works. And the big issues were that the algorithms were limited. So pose detection actually was really terrible, and any individual frame was not so good. But over time, you could accumulate evidence, and that would be good. And the other issue was that there was a lot of limits to how much data you could find, and there were just not many sources of data. And so I did my postdoc sort of 4 or 5 years later. And in the meantime, of course, the algorithms are way better. This actually works pretty well in the wild for pose detection. But the data is actually kind of limited at the same time, though. So the data hasn't made a lot of progress. And the actual reason why this is the case is because the standard way to collect data is to be very explicit. So if you've collected a data set yourself, you probably have remembered this process where you sit down in an office and you say, oh, we're going to make a data set. And it's going to be everyday interaction data set. And you make a big list of what you want. Get out of bed, brush teeth, pour coffee, open refrigerator, so on and so forth. And you just sit down and you make it. And then someone goes off to YouTube and they search for these things, and then they collect the data, and everyone's happy. So for example, opening a laptop. We want to watch and we want to see how the state of the laptop changes. We can reconstruct it. This will be great. Oh, wonderful. Best paper award. And then you go to YouTube and you find out that when you search for opening a laptop, it's about how do you open a laptop to replace the RAM. In fact, basically anything every day, if you just search for it on YouTube, you find the funniest stuff. It's really actually kind of entertaining, and you should try to do this just to see what you find. And the reason why this is the case is you have to remember how YouTube data works. So some random person with a YouTube account says, I have a great video. I'm going to upload it. And they have to care to upload it. Then they have to care to tag it. And they're going to put some tags so that they get views. Maybe they're going to go commercial. Maybe their channel is going to blow up. It's going to be great. And then some vision person comes along with a web scraper and then just finds it by your tag. And so when you have a video like this, if you want to see someone open a laptop, if you upload this and tag it, unless this is art, you need a new hobby. This is very boring. And then if you actually expect to find this sort of data of people beautifully opening objects and tagging them I am opening a laptop, it's just not going to happen. And so this is a big problem that people have faced, and actually there's not a very good solution for finding these everyday things. So we have a different way to do this. And so it's actually, if you haven't seen these before, after the talk, you can go to YouTube and search for my daily routine. And you'll find thousands and thousands of videos. And if you look inside of them, they contain things like, for example, getting out of bed, spreading Nutella on toast, opening refrigerators, closing doors, all sorts of interesting everyday interactions. But they're not tagged. No one uploads a video which says, I spread Nutella on toast. I then open the refrigerator. It's tagged as my daily routine. And I'll show you one of them, since it's worth watching or listening to. I don't know if I have mute. Let's see.
Hi, Logs.
Okay.
Welcome back to my channel. So today
So this is the start of it. It's 15 minutes of it.
Morning routine, and this is my fall routine, and it's pretty much how to start my day off whenever I'm going to be filming.
So she does this professionally, actually. So a lot of these people are professional.
Get started. So I usually get out of bed normally around 7 or 8
Note the follow me
o'clock, but
and like sort of
lately,
Instagram,
I've been
Snapchat.
waking up super late for some reason. Even my alarm clock doesn't wake me up anymore. So by around 9 o'clock is really when I get out of bed. And lately, I'm also trying to not be on my phone so much in the morning, like, right when I wake up. So here I am, pretty much just checking the time and then getting out of bed as soon as possible. And then I go on ahead and make the bed because I got these new comforters set and
And it's likely that there's a link with an affiliate tag that she's selling that, where you can buy this on Amazon. Okay, so that's like, and there's 15 minutes of this. And so it's actually, the reasons why people upload this are actually fascinating. And it's about, we can talk about it afterwards. It's about trying to like show how normal and in control your life is. And it's actually very interesting. But basically you can see that there's stuff like, for example, getting out of bed that she's filmed herself doing. Of course it's all acted, but it's wonderfully done acting, and they're not focusing on the details of how do I get out of bed. What they're trying to do is tell a story about how their life is very nice. And so because they're not focusing on that, the actual acting is quite good. But there's also junk, like, for example, panning across the bed, which we don't want. And so the way this works is someone watches a bunch of these and makes a bunch of queries that you're going to search for. You get 2.5 years of footage from YouTube by searching for stuff like this. And then no one's going to watch that, so what you do is you have a computer watch it. And instead, a human looks at maybe 1,000 or 1,500 of these videos and makes judgments like this is good, this is bad. And by good and bad, I mean that someone interacts with objects in this video. And then the computer watches 2.5 years of footage and does stuff like shot detection and actually looks through the footage to make sure to get rid of most of the obvious junk. Then finally, you give it to a set of crowd workers, and they watch maybe 16 days of footage to get rid of the last bits of junk. And so this produces a data set which consists of people interacting with the world. And it's a data set which we call a vlog because these things are called lifestyle vlogs. And so why would you actually do this? Because this seems a bit complicated compared to just searching and downloading. And the reason is it's more effective. And so if you look at this everyday interaction stuff, you could first of all have your students do this. And then you can get maybe like 10 hours of footage. And from as many students as you have, and maybe their friends. So it's not very scalable. On the other hand, if you hire people off the internet, you can get this a bit bigger, like 100 hours. But still, the number of people who are going to sign up to do this is kind of limited, because it's like, why does a research company want to film me in my home doing everyday activities? But on the other hand, if you actually just find something which organically happens and then mine it, you can actually get like 3 times as much footage from 10 times as many people, and you don't actually pay people to collect each individual data point. So before labeling, all these other methods, you have to pay money to get the data before you even label it. And so this is very much unscalable. And so we have hundreds, like 344 hours, but to convince you that it's not junk, we can just look through some of it. So here's a picture from the start of the talk. Like if we take the fridge, well, okay, how many fridges do we have? We have 400 times four times as many fridges compared to sort of competing data sets. And so if you look at what the fridges look like, they have a particular bias in terms of this is how people tend to depict them in lifestyle videos, but you can see that it's actually quite good data. And I'm not saying that this is a magical solution for all your problems, but it's a good way of getting data that's actually quite clean. And so, of course, one thing that happens is that obviously there's a demographic bias, and there's also a bias in terms of the houses that you see, and these things tend to be quite edited, so the clips tend to be quite short. But it's quite good data. But there are reasons why you would actually not want to gather them by having a list of things. So if you have, like, for example, a microwave, like you say, oh, we have a demo. We want a robot to like open a microwave. This will be a great demo. Everyone's going to love it. So you go to the internet, you find a data set. Well, if you have one of these other data sets, well, it turns out if you make a list, you sometimes forget stuff. Like charades, for example, doesn't have microwaves or ovens. And so you don't actually have these demonstrations. And we didn't search for any of this, and we still find them. And so if you look at these microwaves, you can see, again, there's certain bias to the way that it's depicted, but it's a large amount of actually quite good data, and we didn't actually search for microwaves. So any particular object in your house that you might care about, it's likely that it appears at least a few hundred times, I would suspect. You just have to be able to find it in the data. Now, there are other reasons why, actually, independent of like not being able to find the data, why you would actually not want to, why I think that actually this idea of collecting stuff with a list is actually problematic. And actually, we actually discovered this when we tried analyzing our own data. And what we did is we said, we want to understand what's going on in this vlog data set. And so we want to know what sorts of scenes happen in the data set. And we say scene classification. Oh my gosh, there's so many papers, the accuracies are so high, this surely works. So what we did is we took the densest, the deepest network that we have, say a DenseNet 161. It's trained to do scene classification on like 2 million images. This definitely will work, right? So what we do is we feed in these images. These are like frames from vlog. And then we get these outputs. And we get like ice cream parlor, biology lab, beauty salon. It loves saying beauty salon with like 99% accuracy. And actually, so if you've done these sorts of experiments before, you'd probably say, well, OK, you probably set the mean wrong, and it's probably just like it's feeding in garbage and it's getting in garbage. So I actually went off and I sat down, I checked the demo code on their website. In fact, they have the upload your image, and actually sat and uploaded a whole bunch of these images to make sure this is correct. I was completely confused by this. Like, this looks like complete junk. And the reason why is that I started looking at the data that they trained the method on. I said, oh, I mean, how hard is it to detect a bedroom? I mean, this is crazy. I mean, it's like 2018. This should be doable. And I looked at the bedrooms that they trained their method on. And so I guess grad students only, or the brave, how many of you make your bed every single morning? Raise your hand. OK, we got one person. Oh, two? Typically, there's one or two, and then they give judgmental looks. All right, how many of you don't make your bed every single morning? You might try some mornings and do it, but often the bed isn't entirely made. All right, no one's brave. But the answer is, I know all of you. I know a bunch of you don't do it. But if you look at actually the data, the vast majority of bedroom images on the internet, the beds are all made. And in fact, they're all taken from the corner from a camera. And this is like it just reminds me of like, oh God, I have to find a new apartment. I'm going to go on the internet to find something on Craigslist. And so it's a very specific angle. There's a lot of bias. These are images which are tagged as bedrooms, which tend to be real estate ads. On the other hand, this is what we tend to get. And so these are the images which are taken in bedrooms as opposed to taken of bedrooms. So these happen to be in bedrooms, but they're not depicting bedrooms. And so you can see that there's obviously it's a different distribution, but it's I think a much more realistic distribution because at least the camera's not in the corner. OK, so that's about the data. We have some tasks that we have labeled the data with. So I'll briefly go over it. It turns out there are too many objects to actually enumerate. So we just focus on the hands of people. So like people and how they interact with the world. So we have an image-based task, which is just how many hands are in contact with the scene. And so this is just like trying to figure out, is a human interacting with the scene? And then we also have like video level tasks, like basically, does a human interact with a cup or a door or a pillow or a bed in this video? And so these are just, you have to sort of look through the entire video and figure out, not only is there a bed in the scene, but does a human actually interact with it? And by that, we mean physically touch it. And so I'm not saying that these are the best tasks to work on, but these are some tasks that sort of the data set comes with. And I'm hoping people will reuse this data set for other things. But you can just sort of watch some examples. And so here is just applying frame by frame the network, which predicts whether the human is touching something. And in the top in the video, I'm showing you the class activation maps of basically where's the network looking to make its decision. And what's kind of fun is that the network ends up learning a detector for hands. And it just learns this automatically. And this is quite exciting because actually the hands come in all sorts of different scales and poses. And it's actually quite difficult to get to work on just on all this data. And in general, this predicting the contact state with the scene does reasonably well. But there's a long way to go, actually. And it actually turns out to be a very difficult problem because you have to distinguish between, is my hand actually touching the screen and is my hand touching the screen? And there are lots of horrible biases in terms of it's a very imbalanced problem. And there are lots of shortcuts that a network will take. So actually, I think it's an interesting problem that we haven't solved yet. We've gotten a little of the way there. But you can imagine having something like, what is a person doing with their hands would be very useful for imitation learning. And so we have lots more of these. OK. So then I just want to leave you with one thing, which is kind of looking towards the future in both ways. And so we have, I think this data set of people doing stuff is actually quite useful. And it's a data set consisting of people doing stuff with their hands, and it's in time, which lets you do all sorts of interesting things. Like you can then take this data set, and just by predicting where the hands are and then training a network to predict where the hands will be in the future, you can actually learn to predict how humans are going to move their hands through the scene. And so this is like a very basic way of modeling how humans will interact with the world and how you can forecast this. And so we have a network which takes in an image and how many frames to jump. So for example, at 2 frames, it predicts a hand segmentation in the future. 8 frames, 16, and 32. And so it's seen lots of people washing their faces, so it does a reasonable job at predicting how she's gonna move her hands. Then we have someone making the bed, 2 frames, 8 frames, 16, and 32, and you can see it sort of gets, it starts off very certain, and then it just has this cloud of uncertainty that grows. And so it can model these sorts of things. But my favorite one of all is, of course, we have someone using their phone, and this is one of my pet peeves, people using their phone at the table. And it's learned a lot of depressing things about humans, which is that if you have someone using their phone 2 frames in the future, 8 frames in the future, 16 frames, it does change if you look at it. 16 frames in the future and 32. And so it's actually learned you can see this is actually quite good model of how people interact with their phones these days. All right, so that's a little bit about the data. And to summarize, what I've talked about is how to infer 3D from 2D. Oh, whoops, sorry, this old slide. I've talked about navigation and how to move out in the world. And I've talked about how do you learn from humans interacting with the world a little bit, but really mainly about how do you get data for it, because that actually turns out to be the big challenge. And so with that, I'd like to acknowledge my sponsors, and of course, all the collaborators who helped in this work. So thanks.
Are there any questions for David? Yes, please.
When you showed your memory, you said you have this Gaussian shape to know which memories you take into account, and how does this practically work?
Yeah, so it's basically a Gaussian. You can think of it as just even though the index is like a discrete thing, you just pretend it goes from 1 or like 0 through n, and it's a Gaussian on those indices. So it basically uses the nearby memories, and I don't remember off the top of my head the scale parameter, but it's certainly a few nearby. Does that make sense? Or
you mean that you use the memory which is at this index, like with a stronger way?
Exactly. Yes. Yeah. So it's basically so that if you're between 2 memories, you combine them, like say 50-50, for example, approximately, and then the other memories nearby contribute a little bit. So it's just, it's a way of having a smoothly varying way of going from one memory to the next, where you don't have this discrete jump. And so essentially it's...
But you cannot add some factor in front of the features or in front of the actions.
You can't add a factor in front of the features.
I mean, you cannot just take half of the feature. I mean, it doesn't make sense.
So the key is that the features are learned so that this works. So that the features it's all learned end to end. So the features are trained in a way where you can actually add them up, and basically you can take a weighted combination of them and have it still work. In the same way that, like for example, if you have like a video, if you take the weighted combination of the features, it's actually a good representation. So and the memories are fairly dense in time. I mean, they're not super dense, but you can imagine that if you're the network, you'd sort of try to put things in different feature vectors, in different dimensions of the features, so that maybe it says 50% restaurant, 50% police station, and the subsequent model can use that as a way of just describing that you should probably see a police station and maybe a bit of a restaurant.
Any more questions?
Yes.
Can you please elaborate more on that study with the navigation? I mean, how big is the training and testing set in terms of how many trajectories you trained on? And
yeah. So we initially trained on about 100,000 trajectories. We've increased it quite a bit. So actually, right now, the reason why I didn't put the exact numbers in is because it's still a bit in flux, but it's substantially larger than 100,000. So we started out with 100,000, which is enough to learn a good model.
And do you control the variability of the trajectory? I mean, the length and the structure of or difficulty level of the trajectory?
So there's a way to control it. The length is 30, but what we found is because it's for the training for all things. But you can test it on, because it's a recurrent model, you can test it on, say, 60, and it does reasonably well. And then the difficulty there is, I don't remember off the top of my head how exactly we control it. But it's basically that you have the distance to the walls and how close that goes to the walls. But you basically start off with a bunch of random paths, and the number of times that you come close to an obstacle essentially tells you how easy the trajectory is, more or less. And I'm sorry I can't give you the exact number of the train set, because actually these results actually just came in just this. Some of the results just came in this morning, and I don't want to give a wrong number as opposed to the right number. But we initially started out with about 100,000 trajectories. And of course, actually, one thing we found is that training for much longer and just sitting around and just letting it run on many, 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 many more trajectories is actually quite crucial for getting the numbers higher. So the 100,000 is enough for OK results, but improving, getting really good results requires just letting it sit and run.
Even with this imitation learning?
Even with this imitation learning. Because it is a very difficult task, and it's also, the big problem is that you do have to do these backward, you have to make sort of reasonable decisions over the entire trajectory. So you can make some progress pretty easily by just doing a simple reactive model, but to actually do well, you actually do have to learn a good model, and that takes a while.
Any more questions? I have one last one. So
Yes.
did you test setup where you train on the SunCG and then you deploy it on the Stanford?
So SunCG, no. Onto Stanford, I would be very curious, because I think going from realistic to synthetic is relatively easy. Synthetic to realistic is a bit hard. We've done a bunch of things where you train on Stanford and then you test on other things. So the systems work on a bunch of these other simulators like Minos, and they seem to work reasonably well. I mean, I don't know the numbers, but it's kind of the type of thing where you watch it and it's like, okay, this works pretty well, because a lot of the behavior is just obstacle avoidance. Some of the earlier setups, I don't precisely remember whether it's Sarb's previous paper, but I think it's actually this paper, because Sarb, we had an Intel demo, and there was talk about trying to get it to run on a real robot. And I believe that this method ran on a real robot for a very simple trajectory. I mean, we're talking about go around a table and then go sort of come back. And I wouldn't deploy it on a real robot, but it does seem to transfer reasonably well, because most of the stuff it has to do is actually quite simple.
Okay, so thank you very much.
Thank you very much.